Hello guys, today I'm gonna do some, we're gonna solve some problems that using the equations of acceleration, of accelerated motion, okay? So in the previous video, we talked about acceleration, we did it graphically, but we did it conceptually, but we didn't solve any problems like with the numbers. So now we're gonna try to do that. And the equations we're gonna be using are in your lavender sheet. This sheet basically is the top three on the left. So the first one says Vx equals Vx0 plus AXT. I'm going to drop the x's. That's just showing that it's one-dimensional. So I'm just going to drop this subscript. So the first one is V equals VO plus AT. Okay, now what's the meaning of all these things? V is a velocity. It's not speed. Okay? Sometimes they are the same thing, but sometimes they are not. The VO is your initial velocity. It means it's like your velocity when the time is equal to 0. A is acceleration and T is time. Now V is your velocity after you have traveled T seconds, after you have traveled this much time. The next one is X equals XO plus VOT plus 1/2 AT squared. Okay? Now X here stands for position. And this will help us find the displacement. If I subtract here, if I do X minus my position when the time started, when the clock started, I will get my displacement. And a lot of times the displacement is the same as the distance traveled, but not always. The next one is V squared equals initial velocity squared plus 2a, and that x minus xo, I'm just going to write that as the change in position, which is displacement. And there is one that's not there, and that one is the change in position or displacement is your final velocity plus your initial velocity over 2. In other words, the average of your final and your initial times the time that you travel. So if you want to find the displacement after you traveled t seconds, you just have to use this formula. Now, I'm not going to show you the proofs to this. Maybe I'll do another video just showing you the proofs for like 10 minutes. It's time consuming. It takes a good 10 minutes to kind of like do it. And I always do the proof. For the most part, I do it graphically. But for now, we're just going to use those formulas and we're going to try to solve some problems. All right. So let's do some sample. Actually, before we do that, let me ask you this question. I want you to think about it before you continue with the video. I want you to pause the video when I ask the question. So let's say I have a car traveling at, let's say, 10 meters per second, so like over 20 miles an hour. And it's going to come to a stop. Okay, so you apply the brakes. It's going to come to a stop after traveling a distance d. Okay? Now, assuming the same road conditions, okay, and I'm going to put my foot on the brake the same exact way, in other words, the same deceleration, but this time I'm going at twice the speed. So instead of 10, I'm going at 20. Okay? And I'm going to come to a stop. So I put the dots because I don't know where I'm going to stop. Okay? And in terms of d, okay, what is my stopping distance? So I want you to pause the video, all right, and think about it. And then once you think about it, you can continue with the video. Okay. So I'm going to see write an expression for my stopping distance here. And the equation I'm going to use is this one here, the one that does not have time in it. So if I do V squared equals VO squared plus 2a delta x. Now, if I'm traveling to the right, and if I choose the location where I put my foot on the brake as the origin in both cases, I hope you can see that delta x is d. Okay? And since I come to a stop after traveling a distance d, this is 0. So if you manipulate this a little bit, you should get this expression for distance. Now let's look at it for this other distance. So let's call this the new distance, right? I do the same concept, but this time the new is going to be, I can do the same process, but the VO is twice as much. So I'm going to put that 2 VO in parentheses and square over 2A. And I can see that the 2 gets squared. So this is going to be 4 times negative VO squared over 2A. Well, this expression here is just D. So if I double my speed, I'm going to need 4 times the distance to stop. In other words, if I was able to stop in, like, let's say 5 meters here, now I need 20 meters. Now, what happens if I make this 30? So I tripled my speed. If you come to this formula, you're going to see that there will be a 3 in here, right? So you're going to come out with a 9. So it's always that ratio square, the ratio between these speeds square. That's your stopping distance. Okay? Now you stopping distance, but the ratio of the stopping distance compared with the original distance. All right, now let's do some problems. And always have the formula sheet with you, and let's figure out which one we're going to use. Okay, actually I'll write these formulas here. We've been doing this for a long time. I have them memorized. And the last one is your final velocity, initial velocity, divided by 2 times time. Okay, so a ball rolling down a hill at 4 meters per second accelerates at 2 meters per second. So we're going to choose downhill as positive. Just keep it simple. Okay, what's the velocity 5 seconds later? So the way you solve these problems, you see what's given, and based on that, you decide which equation to use. You might come across problems where you might have to use 2 equations, but that's pretty rare, maybe not. You can probably just get away with it with just doing 1 equation. All right, so this is my initial velocity. See this, the units for this, it's meters per second, meters per second squared, that's acceleration. Okay, what's the velocity 5 seconds later? So we're basically looking for the V. So if I look at these equations, I would use the first one, and I'll let you do the math. That's too simple. Okay. Example 2. You know what I'm going to do here? I'm just going to show you which equation to use, and you decide which one, how to do the math, okay? A car traveling at this speed, so we're going to choose the direction of travel as being positive all the time. Keep it simple. So this is VO, this is the acceleration, this is the time. It's asking me what's the displacement, so it's looking for the delta x. Now which one will do it? It looks like it's the second one here on the board. Am I right? Yep. The displacement of a car going from 20 to 30 meters per second is 100, so this is delta x. Initial velocity, final velocity, what's the acceleration? So we're looking for A. So it looks like time is not even mentioned in here, so I'm going to use the one that doesn't have time in it. 4. A body going at 10 meters per second, so that's my initial, experiences an acceleration of 6 meters per second squared for a displacement of 100 meters. The displacement is just not, it's not x, but it's delta x. But a lot of times what do? We choose our origin to be, our x0 to be 0. So the displacement and the position are equal. How long? Now, a lot of times people confuse how long with like distance, but that's how long means how much time. It's time, it's not a distance. So we're looking for time here. Now, if you look at the equations, it looks like the one that doesn't have the v in it is the one that's going to cut it for us. So it looks like we have to use this one, right? Yep. So that's the one we're going to use. So I'm going to write 150 equals 10, 10 times t plus 1/2, and this is after you write the equation, obviously, t squared, okay? And you're probably going to end up with like a positive and a negative answer, so you just drop the one that's negative. Now, if you don't want to use this, you might have to find the v and then use another equation. Okay, next equation, question. This is example 5. Now, when it says here uniformly accelerated motion, that does not mean that the motion is uniform. Uniformly accelerated motion means the acceleration remains constant. So don't confuse the two. Don't make that mistake. A car starts from rest. Thank you. The VO is 0, moves with a constant acceleration. Now, that's not constant velocity, it's constant acceleration. In other words, the acceleration does not change during this motion and covers a distance of 64 meters. So this distance and the displacement are the same. So I'm traveling down a straight line. I don't make any turns. I don't come around. Okay? So the distance and the displacement are the same thing. So I'm going to call this delta x, and this is my time. What is its final speed? Now, before we do that, actually, so I'm traveling 64 meters, right? And I'm going to do that in 4 seconds. And I want you to think about this before you continue the video. So pause after I explain the problem. After 2 seconds, will I cover 32 meters, meaning like half the time? Will I cover 32 meters, less than 32 meters, or more than 32 meters? Think about that. Okay, I'm going to continue. At 2 seconds, okay, in other words, in the first 2 seconds, you're going slow. And the last 2 seconds, you're going pretty fast. So the majority of the 64 meters is going to be covered in the last 2 seconds because your velocity is pretty high. So in the first 2 seconds, after 2 seconds, you would have covered less than 32 meters. All right. So now let's go back to the problem. What is the final speed? So velocity, speed is the same thing. We're not changing direction. We're just gonna, everything is positive to the right. So if I'm looking at this, it looks like, which equation will do it? It looks like it's the last one. Delta x equals v plus VO over 2 times t. And this is 64. This is gone. This is v over 2 times 4. So it looks like v is 32 meters per second. That's what it should say down there. Yeah. For b, what is the distance covered in 1/2 the total time? So we say it's not 32, right? It should be less than 32. All right. So now my time is no longer 4 seconds, but it's 2 seconds. Okay. Now, you have to be careful. I cannot use this number. This is my velocity after 4 seconds. Common mistakes. After 4 seconds, I'm going this fast. So I cannot use that after 2 seconds. What else do I have? Oh, I'm doing the, oops. I'm supposed to do the acceleration first, sorry. Okay. So which one is going to do the acceleration? It looks like I have choices here. So I can probably just use the simple one, which is the first one. Okay, so the initial velocity is 0. This is 32. But that happens after 4 seconds. So the acceleration is 8 meters per second squared. Now, fact that it says uniformly accelerated motion means that this acceleration can be used over and over and over. So you own this. This is something you can use for all the parts of the problem. For part C, what is the distance covered? So this is what I was talking about. Okay. In half the total time, so the time is 2 seconds. I cannot use the 32 because that's happening after 4 seconds. That's your velocity after 4 seconds. I can use the 8. So what I can use here is I can do the 2 seconds. I can do the acceleration. I always need 3 things before I can solve. So I have the time, I have the acceleration, and I have the initial velocity. And I don't know the velocity at 2 seconds, so I'm going to use the one that doesn't have velocity in it. So it looks like the second one here, the one with the square, the time square. So delta x equals VOT plus half AT squared. We're looking for this delta x. This is gone because that's 0. Don't just get rid of the VO and keep the 2. I've seen that happen before. Okay, the whole thing is 0. It's 1/2 8 times 2 squared. So you would have traveled, what is that? That's 4 to 16 meters. And the last question, what is the speed when half the total distance had been traveled? So we're looking for V when delta x is 32 meters. Now again, we can use this acceleration, okay? We can use the delta x and we can use VO. I cannot use this 16. I cannot use the 32 because the 32 happens after 2 seconds. All right. So let's try the one that's probably try the one with the V's square. Okay. This is gone. So V square equals 2 times 8 times 32. Okay. So we take a square root, do plus or minus. In here it doesn't matter because I'm traveling, let's say, to the right, right? And the right is positive, so I'm just going to pick the positive answer. But later on, when we do free fall, we throw things up in the air and we let them fall, it's going to matter. And we'll get to that in a later video. So I'm going to cheat. Actually, the answer is down there. 22.63 meters per second. See how fast I could do mental math? I just looked down there. Okay. Let's look at your favorite. All right. This is a problem where you have to draw a VT graph from an acceleration time graph, and you have to explain. So the explanation I'll just do verbally, okay, and we'll do the drawing. I'll talk a little bit about the drawing. So this is an acceleration time graph. It looks like you have a positive acceleration, but it's a slow rate of change of velocity compared to this one, right? So in here, you have no acceleration. It doesn't mean you are not moving. Okay, you could be not moving, so I'm just going to say that I'm moving. So I'm going to put a velocity here that's constant for that little piece, okay? And I'm going to accelerate, but at a slow rate, so which means not a very steep slope, because I'm going to leave the steep slope when I do this. And then I go at a constant velocity again. Right? And then I accelerate at a higher rate than previously. So maybe I'll make this one a little steeper. Okay? And then I go for a little bit at a constant velocity. That's it. Okay? So I hope you heard the verbal explanation, and you can put that in words and put it down there. Carmela and Desi leave a parking lot separately and drive west. They both start from rest. Desi leaves first, traveling with an acceleration of 4 meters per second square west for the first 6 seconds, and then driving at constant velocity. Okay. 2 seconds after Desi starts, so there is a delay. Carmela starts with an acceleration of 3 meters per second square west for 10 seconds, and then she drives at a constant velocity. Graph the velocity of both travels as a function of time up to 16 seconds, so the whole time we have here. Starting at time t equals 0, when Desi leaves the classroom. Okay, so you know what? In here we're going to use west as positive. It's a choice, okay, since they only given us the positive side of the graph. Okay, traveling with an acceleration of 4 meters for the first 6 seconds. So for the first 6 seconds, I have to have a slope of 4. Is that right? Yeah, I have to have a slope of 4. So how do I do that? I don't feel like doing the calculations. Let me just see what I did here. So what I did, so for 6 seconds, I can do a rise of 24 over 6. So I estimated what 24 is about. Okay, and I draw a line here. So that's an acceleration of 4. So it's a slope basically. It's 24 over 6, and then constant velocity after that. Okay. The other person leaves 2 seconds later, so they're going to start here at 2 seconds. So this one is this. Okay, and the acceleration is 3, which means a rise of I don't know. Did I do a rise? I did a rise of 30 over 10 seconds. Okay, did a rise of 30. She does it for 12 seconds, for 10 seconds, so she's going to go up to 12. So 30, yeah. So it's 30 over 10, yep. Okay, and then continue at a constant velocity. And this is Carmel. Okay, and the explanation is, the reasoning is what I said verbally. Alright, I'm going to stop this video here, and I'm going to do the problems in a different video. Alright, thank you.
Is it gonna stay?
It's recorded?
Yes, but it's falling down. There we go.
It's recorded?
Yeah.
Alright, good. Guys, welcome back. This is a continuation of Accelerated Motion 2, the video that says Accelerated Motion 2. Now we're going to just do problems. It's about 7 or 8 pages of just problems. Now, to keep the video short, I'm not going to do the calculations. I already have them down here. So I'm just going to tell you how to do the problem. And I'm sure you can just put things in your calculator and figure out the answers. So I'm on page, what page is? I'm on page 13. And I'm doing problem number 1. So it says a race car can be slowed with a constant acceleration of negative 11 meters per second squared. Now, they don't have to tell you the negative. So if it says that it's slowing down and you're assuming that we're going in the positive direction, that has to be negative. The car is going at 55 meters per second. How many meters would it take to stop? A good strategy for these problems, for all of these problems, is to figure out what is it that you have. And then look at the equation that links all the things that you have and the one that you're looking for. So I'm going to write the equations here. The first one is V equals VO plus AT. The next one is X equals XO plus VOT plus half AT squared. V squared equals VO squared plus 2A displacement or change in position. The last one is displacement is the average of your initial and final velocities times t. All right, so for this one I have the acceleration, okay? I have my initial velocity, and it comes to a stop. Not everything is given in numbers, but a lot of things are given in words. So that's, that's the v, which is equal to 0. Comes to a stop. And it's going with a constant acceleration. It doesn't mean that it's a constant velocity. It just means that the acceleration does not change. And the question is asking how many meters. So in this case, the displacement and the distance are the same, because we're traveling to the right. We're not changing direction. We're not coming back. So we're just going in a straight line. So the displacement and the distance are the same. So in order to solve this, you just have to figure out which one of these equations links all those four things, because you're looking for this, right? And if I'm looking at this, it looks like it's the one that doesn't talk about time at all. So I will be using the third one. I'll label this 1, 2, 3, and 4. So I'll be using the third one. So I will go v squared equals v0 squared plus 2a delta x. I'm not going to write the equation going forward, so but you have to write it in your when you're doing your homework. This is 0. This is 55 squared minus 22 delta x, and you can do the math, and you should get delta x equals 137.5 meters. And the answer key is on your last page. All right, next problem. So I'm just going to give you a quick hint on how to do the problems. Highway safety engineers built soft barriers so the cars hitting them will slow down at a safe rate. A person wearing a seat belt can withstand an acceleration of negative 300 meters per second squared. Now, if this says positive 300, you will have to make that negative, because what's happening, you're hitting the barrier and you're slowing down. And we're going to look at the direction of travel as positive, but you're slowing down, which means your acceleration is negative. How thick should the barriers be to safely stop a car that hits a barrier at 110 kilometers per hour? Now, you got to pay attention to the mixed units. This is in meters per second square. This is in kilometers per hour. So I'm going to change the kilometers per hour to meters per second. I've already done that, and I'm getting about 30.56 meters per second. Now, when you're doing the calculations, don't use 30.56. Use whatever you got in the calculator when you did the conversion. So this is VO. The final is 0. This is my acceleration. And it's asking how thick, which means it's asking for the distance it's going to travel before it stops, once it hits the barrier. So this looks like exactly like number 1. So I have to use the third equation, set V to 0, set VO to 30.56, and I'm not going to keep doing it because you know how to do the math. Third one, okay, a car traveling at this speed, so that's your initial, okay? When the driver sees a child standing in the road, he steps on the brakes and slows at 7 meters per, negative 7. So even if it says 7, you have to make it negative. So this is the acceleration. How far does the car go before it stops? We ignore a reaction time. We'll do some reaction time problems later, where we have to consider the reaction time, because there will be a certain distance traveled while he's reacting. So we're looking for the delta x. Okay, so what do we have here? And he stops, so the v is 0. It's the third equation again, just like number 2. You can figure out the math on your own. Actually, I just want to mention one thing here. So when I'm using this equation, the third, so I'll put 0 here for v. I would put 20 for VO, and then I would do minus 14 t. The 14, or the negative 14 comes from 2 times negative 7. You just got to be super careful. I've seen people do 400 minus 14. It's like nonsense. We shouldn't be making this mistake in an AP physics class. All right, number 4. I'm going to talk a little fast and do this math. An engineer must design a runway to accommodate airplanes that must reach a ground velocity of 61 meters per second before they can take off. So this is the takeoff speed. That's the V, not the VO. Okay? These planes are capable of being accelerated uniformly at a rate of 2.5 meters per second square. So that's the acceleration. And here it doesn't say it, but the plane is starting from rest, basically. Right? So we're going to say VO is 0. Okay? How long will it take? How long means time. So we're looking for the time. So we have to figure out an equation that kind of links VO, VA, and T. In other words, we're looking for an equation that doesn't have delta X in it. So if you look here, the one that doesn't have delta X, hey, it happens to be the simplest one. So we're just going to use V equals VO plus AT, right? And if you do the math, you should get, you should get 24.40 seconds. Now, so now you found the time. Time is 24.40 seconds. Now, what must be the minimum length of the runway? So we're looking for the delta X. Now, all you need to solve these problems is 3 known variables and 1 unknown. Now here, you have 4 known and 1 unknown. You have the time, you have the VO, you have the acceleration, and you have the V. So at this point, you have choices. Just make sure you pick the equation that has delta X in it. In other words, you cannot use the first one, but you can pick any of the other ones. So what I would recommend is pick the simplest of all of them. And it looks like the last one is the simplest. So we would just do a V, which is 61, VO, which is 0, divided by 2, and multiplied by 24.40, and you should get your answer. And your answer is 744.20. All right, next one. Okay, so you're given an acceleration time graph, and we assume an initial velocity of 3, positive 3. Okay. What is the acceleration when t equals 3 seconds? All you have to do is just read from the graph. So 3 seconds is about there, 4 seconds is about there. So it should read -6. You just read from here and come across and figure out the acceleration. What is the velocity when t equals 4 seconds? Now, in an acceleration time graph, the area gives us the change in velocity. Okay? We get the change in velocity. Remember that PVA thing? If you're going in this direction, if you do the area, you get the change in these quantities here. So in an area time graph, you get the change in velocity. So if I do this area, and I do this area here, and I consider this negative and this positive, so this looks like it's 18, okay? And this looks like it's, you go from 2 to 4, that's 2 times, so this is -12, okay? So there is a change of 6, okay? And I already started with an initial speed of 3. So I started with 3, and there is a positive change of 6, so now I'm going at 9. This one is a little tricky, but I'm going to set it up and you can solve the equation. A UPS truck starts from rest, so the V0 of the UPS is 0 meters per second, and accelerates, so this is at 4 meters per second squared, so this is the acceleration of the UPS truck. A Mustang starts 8 seconds later, which means it's going to take less time. Later does not mean more time, so you subtract, okay? You subtract from the Mustang or you add to the truck, okay? It starts from rest also, so the initial velocity of the Mustang is 0. And from the same position, so at least we're starting from the same origin. And accelerates at 7 meters per second squared, so that's the acceleration of the Mustang. How long does it take the Mustang to catch up to the truck? So meaning like time. Okay. Robert, can you check, make sure it's recording? Okay. So when the Mustang catches up to the, thank you. When the Mustang catches up to the truck, they have the same position. So I can say that the position of the Mustang is equal to the position of the truck, or the UPS I call it. Okay. Now it says how long does it take the Mustang, so I'm gonna set t as the time for the Mustang. So they both starting at the origin, they both starting with no initial velocity, so I can just write that 1/2 the acceleration of the Mustang times the time square equals 1/2, I'm using equation 2 without the first two terms. 1/2 the acceleration of the UPS truck. Now, if it takes the Mustang t seconds, it should take the truck t plus 8, because the Mustang starts 8 seconds later. Or I can write it with t minus 8 here and t over there. But there's a trick to that. When I finish this, if I do t minus 8 here, right, I'll have to make the adjustment when I get the answer because there is an 8-second difference. Okay, so this is going to be t plus 8 squared. Now if you do the math here, you should get a time of that was 24.78. So 24.78 seconds. And the way you would solve this, you can FOIL, you can do a quadratic equation, or you can just like plot this in the calculator, put this in the calculator, graph them, and figure out the intersection point. And that's your answer. Number 7, a car travels at 15 meters per second for 10 seconds. It then speeds up with a constant acceleration of 2 meters per second squared for 15 seconds. And finally, it slows down at a constant deceleration of negative 1.65. Now, they might just say it slows down with an acceleration of 1.65. They wouldn't even mention the negative. It's your responsibility to know that you have to put a negative in there. Because now you're traveling in the positive direction, but you're slowing down, which means your acceleration is opposite the direction of motion. So we talked about that earlier in the chapter, actually this part of the unit. What is the final velocity at the end of this time? Okay. Now, you have to use these equations in different time intervals because the acceleration is different from one place to another, and there is no acceleration in the beginning. Period. Okay. So the way I do this, I'm going to show you two ways. I do a timeline, and I say I'm starting here, and I put all the important times where changes happen. So 10 seconds here, okay, and then it speeds up with a constant acceleration for 15 seconds. So this is 25 seconds, and then finally slows down for 12 seconds. So this is 37 seconds. In this phase here, I'm going at 15 meters per second, okay, for 10 seconds, right? Now, if you do the formula, actually, let's do the formula later. So here, I'm going at 15 meters per second. So this 15 meters per second becomes my initial velocity for this phase here. I'll call this phase 1, phase 2, and phase 3. Okay? Then I will find my velocity here. Then that becomes my initial velocity for this last phase. All right, so let's try that. Here I'm going at 15. The deceleration is, or actually we accelerated it, 2 meters per second square. So I have my initial, I don't know my final, and I know the time. I do this for 15 seconds. All I need is 3 things to figure out the 4. Okay, so I have the acceleration, I have the time, and I have the initial velocity, and I'm finding the v. Okay, so I'm going to pick the one that links all those. So it looks like it's going to be the simplest one. It's going to be this first one. So if I do this equation, okay, if I want to find v, I do 15 plus 2 times 2 times 15. So what is that going to be? 15 plus 30, so that's going to be 45 meters per second. So this is 45. Now that becomes the initial velocity for the last phase, where the acceleration is negative 1.65 meters per second square. and the time is 12 seconds, okay? And we're trying to find the velocity here. I would use the same equation, except the initial now is 45, so I would do the same thing, and you would get V equals 45 plus 2 times negative 1.65 times 12 seconds. And you should get an answer of, let me cheat here. You should get 25.2. 25.2 meters per second. Okay, so that's 24. Let me just do the math here quick. So it's 45 minus. Oh, I don't know, why did I put a 2 here? No, I shouldn't have a 2 there. Yeah, that's why that's why it looked weird. 2 minus 12 times 1.6. Yep, that's it. So the 2 was not supposed to be there, my bad. Okay. What's the final displacement? So you basically just have to find this distance, and this distance, right? How do you do that? Well, since I already found the velocities, this distance is easy, right? So you're just gonna do V equals D over T. And if you do the math here, you should get 150 meters. For the second phase, I would just use the fourth equation. It's pretty simple. It's the simplest one that has delta x in it, which is distance in this case. So we just add up these two speeds, divide by 2, so find the average of those two. What's the average? So is that 25 it looks like? No. 56, I can't think. Yeah, 30. So 30 times whatever time you got there, what is it, 15? So 30 times 15 is, what is that, 450? Okay? And then we do the last part the same way using that simple equation. And that's it. Now, here's another option, which some of you might like, some of you might not. So it's really up to you. It's good to have options, have choices. The next one is like, how about if I draw a velocity time graph? I sketch it. Okay? And in the first, so my times are 10 seconds, 25 seconds, and 37 seconds. And I say, you know what? Initially, I'm going at 15. Okay? And I'm going to accelerate at 2 meters per second. So for 15 seconds, so which means I'm going to pick up an extra 30. So after here, so I'm going to be at the 45. So it should look something like that. Okay? And for the next phase, I'm going to lose, from this 45, I'm going to lose 12 times 165. So which is 12 times 1.65. If I lose that from the 45, I'm down to 25.2. So I'm going to drop to 25.2 here. And here, right? Okay. So this lines up with that. This lines up with this. This lines up with that. Okay, this lines up with 10. Okay? And this lines up with that. Now, we got the speeds. Now, if you want to find your displacement, you just find the area here. So some people find this easier, but it's really up to you. I'll leave that up to you. All right, next one. Next, and number 8, I'm not going to do. It's pretty similar to number 7. Number 9 looks too simple. So the answers are on haiku. There's an answer key, but I think it's too easy. So let's just look at something that's a little more challenging. Let's look at number 10. A speeding motorist traveling at 120 kilometers per hour passes a stationary police officer. The officer immediately begins pursuit at a constant acceleration, 10 kilometers per hour per second, which means he picks up 10 kilometers per hour every second. How long will it take the police officer to reach the speeder, assuming the speeder maintains a constant speed? How fast would the police officer be traveling at this time? So let's attack the first question. Time. How long? So when the police officer catches him, they have the same position. So I can say that the position of the police is equal to the position of the car. Okay? Now the position of the police, if we choose the moment, or the position, the place where the car passes the cop as the origin, the x0 is 0. This guy is starting, the police officer is starting from rest, so it's going to look like this. 1/2 the A of the police officer times t squared equals. Now, they would be traveling for the same amount of time when he catches them. Now, for the car, it's going to be, it should be, he's traveling, yeah. Oh, actually, for the car, it's pretty straightforward. It's like there is no acceleration. He's going at a constant speed. So his distance traveled is just his velocity times time. Now, time can be either, if you solve this equation, time can be either 0 seconds, or after you plug in the numbers, you should come up with 24 seconds. Okay, now we have to drop this. This just means that's the math in two places. This is when the car passes the police officer, and this is when the police officer catches up to the car. Now, how fast is the cop going? Well, all we have to do is V equals VO. This is for the cop, for the police, plus A police times time. When the police officer starts from rest, his acceleration is 10 kilometers per hour per second, so which means that this speed is going to be found in kilometers per hour times 24 seconds, and that should give us 240 kilometers per hour. A little fast, officer. All right. G stands for 10 meters per second squared. Okay, so let me see if we want to do that, if it's too simple. Yeah, that one is, I think it's a little too simple. So we're going to use the equation that has the V squares and doesn't talk about time. All right. The police officer chasing someone else this time. So they're starting from the same place. The police officer was stationary, which means he starts from rest. How long will it take the police officer to reach the speeding car? So we're going to say that the position of the police officer equals the position of the car. For the police officer, we use equation 2. And it's going to be 1/2 the A of the police times time square equals, for the person to go in a constant, oh, they're accelerating. Oh, the police officer accelerates. Yeah, this guy doesn't accelerate. Okay, so that's going to be just the velocity of the car. But here's the trick. It's the time it takes the police officer plus 1.2 seconds. Right? Because the car would be traveling an extra 1.2 seconds because the cop started like 1.2 seconds later. Now, if we do the math here, we should get time equal to 21.14 seconds. Okay. How fast would the police officer be traveling at the time he reaches the car? All you have to do is plug it into the first equation. Initial speed 0, acceleration 4, time is that much, and you're done. What distance would the police officer have covered? I would probably do, since I already found how fast, I would probably just use the last one here. That's the simplest. Because I have my speed from B, I have the initial, which is 0, I have the time, yeah, I can do that. I'm going to skip 13, we're probably going to do that in class. Reaction time problems, maybe I'll just do one and you'll have to do the rest. They're pretty much all the same. Okay, so I'll just do number 14 with the reaction time, and you can figure out the rest. Alex is driving down Knickerbocker at 15 meters per second when he sees a deer in the road, 25 meters ahead. It takes him 0.67 seconds to step on the brake. That's a pretty bad reaction time. Okay, he slows at a constant rate of 8.5 meters per second square. Now he's going in the positive direction and he slows down, which means the acceleration has to be negative. So even though it doesn't say negative, you have to make it negative. Okay, until he comes to a stop. Does he hit the deer? Now I want you to pause the video, right, and think about it. Think of a plan. How are you going to handle this? And I'm just going to keep going, but pause the video. All right. So the way I do this is like, okay, I say there are 3 things happening. He sees the deer, right? Brakes and stop. Okay. See a little car. Okay. Now we're going to figure out this whole distance between seeing the deer and stopping, and we're going to compare that to 25. If it's more than 25, it means he hits the deer. If it's less, then the deer lives. So he's going at 15 meters per second here. He's also going at 15 meters per second here. And he's going at 0 meters per second here. There's no acceleration here. There's an acceleration of negative 8.5 meters per second squared. What else? Here we have a reaction time of 2/3 of a second. So I think if we do the simple equations, because this is constant speed, constant velocity, we can do V is d over t. And if you do the work here, you get d equals 10.05 meters. In this part here, to find the delta x, right, which is the same thing as distance in this case, you would just use the equation that doesn't have time in it, so which means the third one, and you would do the work, and we'll get a delta x equals 13.24. So between seeing the deer and stopping, Alex needs the sum of these two. So all you have to do is take the sum of these two and compare that to 25. Now I can see clearly, I don't have to do the math here, I can see that it's less than 25. This is in meters, right? Which means that he stops before 25 meters, which means he stops before 25 meters, which means that the deer lives. Alright? So we're done with this video. I'll make another one and I'll just keep adding them. Maybe the next one I'll call it, this one I'll call probably accelerated motion 3, and the next one will be 4, and we'll just keep going with that sequence. Alright, thank you.